Hi dear students. Dear students, in the previous part of the video, we have discussed about some basic terms of chemical thermodynamics, and there in that lecture we particularly discussed about the various components of the solution and different terms used to express the concentration of the solution like molarity, molality, mole fraction, etc. Dear friends, in the previous part of the video, we also discussed about the definition of colligative property, and we came to know that the colligative property depends upon the relative number of solute and solvent present in the solution, means it depends upon the concentration of the solution. Dear friends, today in this part of the video we are going to talk about the first colligative property in this chemical thermodynamic, which is entitled as the lowering of vapor pressure. So dear friends, first of all we should know what is vapor pressure, and then we will talk about the lowering of vapor pressure as well as relative lowering of vapor pressure. As here in this part of the video lecture we are also interested to study about the relationship between relative lowering of vapor pressure and the concentration of the solution. So first of all, you should know what is the lowering of vapor pressure. Suppose, dear friends, here I will consider this is a one beaker in which a pure solvent is taken and which is volatile in nature. Whenever we will have some temperature, then this solvent molecule will be converted into its vapors, and if this beaker is closed from outside, then these vapors create some pressure on the surface of liquid. This pressure is called as the vapor pressure. So here whenever we want to define the vapor pressure, it is simply defined as the pressure exerted by the vapors of the liquid on the surface of the same liquid is known as the vapor pressure. It's very simple to define the vapor pressure, and I hope you got the clear idea about the what is vapor pressure. But dear friends, what happens, suppose in this beaker I have only a solvent molecule, and in the another beaker suppose I have a solution of particular solute which is prepared in the same solvent. Now in this type there are two types of the molecule. One is here in this type, the two types of the molecule, one is the solvent, another one is the solute, and in this type only solvent molecules are present. What happens whenever these two beakers are closed from outside? From the top, definitely the vapors of the solvent molecule will create some pressure on the surface of the same liquid in both the cases. But what happens actually in this case, large number of the molecules are present at the surface of the liquid, hence the large number of the molecules are converted into vapors, and hence there will be the large pressure created by these vapors on the surface of same liquid. But in this case, some molecule at the surface, two types of the molecules are there. One is the solvent molecule, another one is the solid particles. Some of the space at the surface is occupied by means of such type of the solid particles which are non-volatile in nature, and that's why if we will compare this with this, here less number of the molecules are present at the surface of the solvent. It's very important, less number of the solvent particles of the molecules are present in this case, because some of the space is occupied by means of solid particle, and that's why less number of the solvent molecule will be converted into vapors, and there will be the less pressure created by these vapors on the surface of the same liquid, and that's why the vapor pressure of solution, the vapor pressure of solution. If we'll compare the vapor pressure, then the vapor pressure of solution is always greater than that of the vapor pressure of solvent is always greater than that of solution. Means on the preparation of solution in the same solvent or in the solvent, the vapor pressure decreased. So this is a simple relationship between what happens about the vapor pressure whenever a non-volatile solute is added to the pure solvent. Suppose here this P0, this P0, or I will like to consider this here, this P0, this P0, this P0 is the vapor pressure of pure solvent, and this P is the vapor pressure of solution. So here, then the difference between the vapor pressure of pure solvent and that of solution is known as the lowering of vapor pressure. And whenever this lowering of vapor pressure means P0 minus P is divided by the vapor pressure of pure solvent, then it is simply called as the relative lowering of vapor pressure. It's very simple to define the relative lowering of vapor pressure. So relative lowering of vapor pressure is the ratio of lowering of vapor pressure to the vapor pressure of pure solvent, means P0 minus P divided by P0. And there is always something relationship between the relative lowering of vapor pressure and the concentration of the solution in terms of mole fraction. Particularly according to the Rolls, actually this is studied by means of Francois Marie Rod, who was a French chemist. He has studied the relationship between the relative lowering of vapor pressure and the composition of the solution, and according to him, the relative lowering of vapor pressure of solvent on addition of non-volatile solute is equal to the mole fraction of the solute in solution. How we can define the mole fraction of the solvent? Because this is one of the method to express the concentration or the composition of the solution. Suppose, dear friends, N1 is the number of moles of the solvent and N2 is the number of moles of the solute. Then N2 divided by N1 plus N2. This is known as the mole fraction of the solute. And here, according to the Rolls law, the relative lowering of vapor pressure means P0 minus P divided by P0 is always equal to the mole fraction of the solute, means always equal to the x2, means N2 upon N1 plus N2. Here it is defined here. This is the case here. So this is equal to x2 is equal to P0 minus P divided by P0. Now suppose we will put the value of this x2 in terms of number of moles, then we will simply get this equation, that is P0 minus P divided by P0 is equal to N2 divided by N1 plus N2. Strictly by talking about the Rolls law, which shows ideal behavior for the it holds a good result for the ideal solution, and real solution shows deviation from the requirement of this law. And so for dilute solution, this deviation is very small and it can be ignored. That's why an alternative equation or the form of product law can be obtained by subtracting 1 from this equation, that is 1 minus this side and 1 minus x2. So by solving this, that is nothing but the 1 minus P0 divided by P0, okay, minus P upon P0. So here it can be solved, this get cancel, 1 minus 1 simply is equal to 1 minus x2, this minus minus becomes plus, so this will be 1 minus x2. So means P upon P0 is equal to 1 minus x2. And here, dear friends, if we solve this, all these terms, all these steps in this case, then we got another form of the equation to represent the Raoult's law, that is P upon P0 is equal to 1 minus x2. So this is the equation for Raoult's law in terms of vapor pressure. So dear friends, there are two methods to measure the vapor pressure or to measure the lowering of vapor pressure. One is the static method, another one is the dynamic method. In the static method, what happens, it used simply the apparatus consists of differential manometer. Manometer means which measures the pressure, which consists of U-tube, and this U-tube is attached to two arms which are having the two taps T1 and T2 attached to the vacuum pump. One arm of the bulb is filled with the pure solvent and another bulb is filled with the solution of the solvent. Then the taps T1 and T2 are open and the air inside the apparatus is removed with the help of vacuum pump to the taps. Pump attached to the taps, difference in the level of the liquid in two arms of the U-tube read with the help of moving telescope. This difference between the level of liquid corresponds to what? P minus P0, and which is the difference between the vapor pressure of pure solvent and that of solution. So here, with the help of difference in the liquid, I will show you how it looks like. This is a simple this is the simple diagram that indicates the apparatus for static method. So here, this method, that is this level simply the difference between this level and this level, the difference between these two level, or the difference between the level of these two liquid is directly proportional to the P0 minus P in the lowering of vapor pressure. It's very simple. So you can observe here, it consists of the U-tube which is attached to two arms, one fitted with the two taps T1 and T2, and definitely one arm is fitted with the bulb containing the solvent, another arm is fitted with the another bulb containing the solution, and whenever these taps are open, the air inside this tube is circle with the vacuum pump, and we are based upon the vapor pressure of the solvent and solution. The liquid in these two arms will be different, and the difference between these two levels is directly proportional to the P0 minus P. It's very simple to define this. Another method for the measurement of vapor pressure is a dynamic method, which is also called as the Ostwald and the Wacker method. Dear friends, in this case, actually this apparatus is shown here. Here it consists of the series of the tubes. This is the tube 1, this is another tube. Here this is the tube containing the calcium chloride, and this tube is containing with the tubes. But here, what happens actually, here in this case a dry air is passed. It's very simple. What happens actually in this case, a dry air, these tubes are filled with the solution, these tubes are filled with the solvent, and these tubes are filled with the calcium chloride, which works as the absorbent. In this case, that is dry air is passed through this tube. Once the dry air is passed through the tube containing the solution, which is prepared in volatile solvent, the dry air becomes saturated. With the vapors of the pure solvent, and definitely there is a loss in the weight of these tubes. Two tubes. So whatever loss in the weight, that is indicated by means of delta W1, this loss in the weight of these tubes containing solution, this loss in weight is proportional to the vapor pressure of solution, means P, loss in the weight. Again, these saturated vapors are passed through the another tubes containing the solvent. Here the vapor pressure of solvent is greater than that of the solution. It means that these vapors are again more saturated with the vapors of the solvent, pure solvent, and the loss in the weight, of this component, suppose it is delta W2, it is directly proportional to what? It is directly proportional to P0 minus P. It's very simple to define. Here you can observe here that is nothing but the P0 minus P, and this is another P. So this is here simply case regarding with this. And in the last, this saturated air is passed through the another tube containing what? Calcium chloride, which works as the absorbent of moisture, absorbent of vapors. So all the vapors are absorbed by means of calcium chloride in this tube, and there is a gain in the weight. The gain in weight here in this case, gain in weight, definitely this gain in weight is indicated by means of an gain in weight or gain in mass is corresponds to what? It corresponds to delta W1 plus delta W2, and it corresponds to what? It corresponds to the vapor pressure of pure solvent. So we got vapor pressure of pure solvent, vapor pressure of solution, vapor pressure of pure solvent, and here this is the case that we are getting, that is P0 minus P upon P0 is corresponds to or is equal to delta W2 divided by delta W1 plus delta W2, which is equal to loss in the mass of the solvent and divided by gain in mass of calcium chloride. So this is very simple method known as Ostwald and Wacker method, and this apparatus is also known as the Ostwald and Wacker apparatus, which is used for the measurement of lowering of vapor pressure. So dear friends, in this part of the video we simply talk about lowering of vapor pressure and the relative lowering of vapor pressure, as well as how this relative lowering of vapor pressure depends upon the composition of the solution, which is given by means of Raoult's law. And in the final we particularly discuss about the measurement of lowering of vapor pressure with the help of static method and the dynamic method. So in this way we have completed, or we have in detail talk about the first colligative property known as a lowering of vapor pressure. So dear friends, in the next part of the video we will resume to discuss about the next colligative property in the chemical thermodynamics, which is entitled as the elevation of boiling point. Thank you very much.